Hello everyone, I'm Fangfang, a professor from China Agricultural University. Today, I'm excited to share with you some of my latest research on multi-energy complementarity, basically how we can better integrate hydro, solar, and wind power for a cleaner and more efficient energy future. I hope to show you the challenge we faced and what we have done so far. Here is a quick overview of what I will be talking about. First, I will give you a bit of background about myself. Then I will walk you through my research contributions, what I've done, how I've done it, and what I've discovered. Finally, I will share some of the honors my work has received along the way. Let's start it with a bit about my background. I began my academic journey at Tsinghua University, one of the most selective universities in the world. There, I earned both my bachelor and PhD degrees. I had the chance to work with Professor Wang Guangqian and later spent time at Cornell University as a visiting scholar. After completing my postdoctoral research at the Three Gorges Corporation, I joined China Agricultural University. I've also served as a vice dean at Shihezi University, and I'm currently conducting research at the University of Cambridge. Each step has helped shape my approach to interdisciplinary real-world energy challenge. Now, let me introduce my academic contribution. In Western China, there is a big push to peak carbon emissions and reach carbon neutrality. Multi-energy complementarity is key to make that happen. But there are big challenges, like overproduced solar and wind energies that can't always be used, plus growing concerns about the environment. That's where our research comes in, to find smart, coordinated ways to manage all these energy sources together. To tackle these issues, we look at everything: natural conditions, engineering factors, and future innovations. Our approach is to improve predictions, coordinate planning, and make sure environmental and economic goals go hand in hand. We are also testing how energy storage and real-time adjustments can make these systems more flexible. The challenge is how to quantify the uncertainty of highly spatially heterogeneous wind and solar resources. The upper figures of wind power and photovoltaic output coefficients verifies the spatial heterogeneity of resources, which affects the planning and scheduling. Wind and solar energy change quickly, sometimes even minutely, while water flow changes more slowly over months and years. So, we built models that can work on both time scales. This helps us deal with daily ups and downs and also long-term shifts from things like climate change. We use the method clustering to group areas with similar weather patterns. That way, we can make a better local forecast. Instead of looking at raw data from hundreds of points, we focus on representative zones to improve accuracy and save time. We tested different models like CNNs, LSTMs, and autoencoders to predict how much wind and solar power we'd get at a specific spot. Then we looked at which models worked the best for different places and seasons. This gives us a toolkit for more reliable forecasting anywhere. In mountain regions, wind behaves differently based on altitude and season. We created a forecasting framework that takes these factors into account. The result? Much more accurate wind speed predictions, especially in tricky locations. Clouds play a huge role in photovoltaic output, so we used ground-based cloud images and machine learning to link cloud types with radiation levels. This boosted our 10-minute solar radiation predictions by nearly 9%, which really helps with short-term solar power planning. We didn't stop at wind or solar. We looked at them together. Using Bayesian models, we combined the forecast and measured how confident we could be in the results. This joint approach helps reduce uncertainty in system-wide planning. Runoff isn't easy to predict year to year. We used pattern recognition to improve long-term water forecasts. Our models outperformed older techniques, especially when it came to predicting extremes like floods or droughts. Now let's talk about how we actually operate these complex systems. The big challenge here is building models that can juggle multiple goals at different time scales, like maximizing power output, minimizing environmental impact, and staying flexible with unpredictable inputs, all at once. And we don't have hours to run these models. We need answers in minutes. So we designed algorithms that are both powerful and super efficient. Our model works across different time scales, from hourly to yearly, and covers everything from individual power units to entire systems. It brings together solar, wind, and hydro in a coordinated way. This big picture view helps us run operations more smoothly and make decisions that balance short-term needs with long-term sustainability. We created a multi-objective model for short-term scheduling that uses the predicted wind and solar input, plus their uncertainty, to guide operations. We look at what the power station wants, what the grid needs, and what users expect. The goal is to generate the most power with the least disruption while keeping everything stable. On the long-term side, we care about things like how much sediment builds up in reservoirs and how ecological goals are being met. We created a model that balances power generation, sediment discharge, and ecological performance. This gives us a more holistic view of how reservoirs should operate over time. Fish care a lot about when and how water flows, so we studied cold water fish spawning behavior and figured out exactly what kind of water rise triggers spawning. Based on this, we built ecological flow rules that help coordinate reservoir releases with natural rhythms. This strategy has already been applied successfully at the Yangqu hydropower station on the upper reaches of the Yellow River. And the results? Pretty great. Experts at the Yellow River Fishery Institute confirmed that our recommendations, like raising water 4 to 6 times during spawning season, match what they've observed in the field. It's a strong validation of the practical value of our models. Sediment management is another key part of our model. We developed a new formula to estimate how much sediment is being discharged and how it moves through the system. This helps balance sediment removal with power generation goals, ensuring that both can happen efficiently without one undermining the other. Last in this section is a technique we call decoupling. It links long-term planning with short-term operations, so strategic goals set for the year can guide what happens hour by hour. That way, we are not just reacting to today's problems, we are staying on track with our long-term vision while staying flexible. Looking ahead, our focus shifts to breakthrough technologies that could shape the next generation of clean energy systems. We are exploring creative energy storage solutions and unconventional water resources. Our aim is to push the boundary of what's possible today and offer practical, sustainable tools for tomorrow. One exciting direction is extracting water from the air using sound. We found that low-frequency strong sound waves can actually help clouds form more efficiently by enhancing condensation. Through lab experiments and simulations, we showed how this could potentially be used for rainfall enhancement, offering new hope for dry regions facing water scarcity, and also a possible way to disperse the clouds so that the photovoltaic output could be more stable. We've also studied different types of gravity energy storage, like vertical towers, mountain rail systems, and deep well setups. Each has its pros and cons. For instance, vertical towers can be widely applied, while deep well systems are a great way to reuse abandoned mines. Our research compares them in terms of power output, energy density, cost, and where they work best. Each energy storage type serves different regions and purposes. Deep well systems, for example, offer excellent performance at a reasonable cost, especially in post-industrial areas. Pumped hydro, on the other hand, is ideal when you have significant elevation differences. Understanding these trade-offs helps us make better planning decisions. To meet energy storage needs in coastal areas, we evaluated nearly 20,000 possible sites for seawater-based pumped storage. After narrowing them down based on cost and practicality, we found 106 top candidates. This technology could significantly boost coastal energy flexibility without taking up valuable land. Climate change is shifting solar energy patterns across China. We discovered that solar output is declining in the northwest, but increasing in the east. These trends are tied to changes in solar radiation and cloud patterns. Insights like these are critical for smart photovoltaic investment and planning for the future. We used a multi-scenario model to forecast how much clean energy capacity China should aim to install by 2025, 2030, and 2060. It's all about balancing ambition with what's realistic, factoring in cost, grid stability, and long-term goals. This model supports better decision-making for sustainable growth. Finally, I would like to introduce my academic achievement. My work has resulted in over 80 publications, including 52 SCI journal articles, which I served as first corresponding author. I've also written a monograph, holding 10 invention patents, and earned recognition as an ESI highly cited researcher. These milestones reflect both academic and practical impact. In the past 5 years, I've led 18 major research projects funded by top national and provincial programs, including the National Natural Science Foundation of China and the National Key R&D Program. These opportunities have allowed us to explore and grow research agenda with real-world relevance. Thanks for your time and attention. My research also involves other fields such as climate change, environmental impacts, and water quality monitoring. It's a big challenge to fully introduce my research within 15 minutes. I tried my best to show an outline of my research. If you'd like to follow up, feel free to reach out via email. I look forward to continuing the conversation.